and welcome to this video short where we are going to overview hashing, hash tables, and hash functions. So a hash table is an excellent data structure that should be used whenever possible in computer science. Right? In fact, there are many people that think if you're writing your code and you look through it and you haven't used a hash table, you've probably done something wrong. Right, and so looking back at some of the structures we've looked at previously, simple arrays and simple searching and sorting algorithms, we found that we could employ some strategies to get some significant and notable time complexity improvements. When we did linear search, time complexity was linear. However, if we used and employed a divide and conquer strategy, we were able to improve upon this and get that down to big O of log of n. Believe it or not, we can do better. And the solution is this magical data structure called the hash table. So what if we knew by asking an oracle or by some magical property, we knew that if we wanted to find a particular data item, it had a pre-reserved spot in our data structure. So we could just simply jump directly to that spot, meaning each place had a reserved location or index in this array, so that whenever we wanted to search for it or see if it existed in that array, we would only have to search one location. Well, that would be great because that would just simply be about one computational step, or big O of one. We could jump directly to that one index and compare the value found there. But how do we know that magical reserved place, and or how could we compute such a thing? Well, that is the basis and the base idea behind hash functions and hash tables. All right, so how does this work? Well, a hash table is really simply just an array which has an associated hash function or hash map. This hash function is that magical oracle. You provide as input a data element to our hash function, and it provides you an index or an address into our array. Right, so it is essentially the reserving entity that will tell us where the data item belongs in the array. So we can directly jump to it in big O of one time. Right, so this is great for storing, retrieving, or changing the values of items within an array. Again, the time improvement is clear, going from linear to log all the way down to constant time. All right, you're thinking, well, what's the catch here? Right, well, there certainly are catches here, but let's look at some of the details and see how hash functions work from an illustrative standpoint. So our hash function here takes data objects, data members, and maps them to a hash code. This hash code in a perfect world is some unique representation of our data object. Then we generally will rescale these values into the length of an array so that it can be provided or facilitate the indexing directly into an array. So here's a good example where we have four data objects, and we're mapping it into a hash table of size 5. So our hash function provides unique hash codes, again, in a perfect world, unique hash codes for each of these 4 data objects. Then we will rescale it, often using a modulus function, which really works well in this particular context, down to the range of 0 to 4, all the valid indexes for a hash table or an array of size 5. Right, so 4 will simply go to 4, 16, right, the modulus or remainder, mod 5 is going to be 1, 68 goes to 3, 125 goes to 0. Therefore, object 4 gets mapped to index 0, so object 4 goes here, object 2 goes here, right? Nothing goes into slot or bucket number 2. Object 3 goes here, and object 1 goes here. All right. Again, if we ever wanted to retrieve object number 1, we don't have to search the array. We can go directly there. If we wanted to search for object 1, we could just jump directly to the 4th index. All we'd have to do is compute the hash function value. Great. So again, what could possibly go wrong here? Well, there are some particular issues here. In a perfect world, we would have a uniform hash function where all of the items would get spread out uniformly or evenly across our hash table. And so this is a great property of a hash function, is that it's going to be uniform or spread the items across our hash table. However, in a perfect world, that's going to happen. However, we don't live in a perfect world. So we have what we refer to as collisions. And so whenever an entity or an object gets mapped to the same bucket by our hash function, a collision occurs. And sadly, these will generally happen in real world scenarios using hash functions. So avoiding collisions is something that can be done, however, is not practical in all situations. Therefore, dealing with collisions and having collision resolution schemes is a really important area of research in hash tables and something that we're going to learn about throughout this chapter and throughout this module. All right, so what are we going to do here? Well, in the next episode, what you're going to do is investigate the different collision resolution schemes and particularly investigate linear probing. All right, well, until then, I'll see you in the next episode. Thank you for joining me.